Hi, I'm Saad and I'm doing my Masters in Embedded Systems from Jönköping University, Sweden. Today I'm going to demonstrate a project which we did in the last semester. I'm in third semester right now, and we did a design, build and test project in semester 2. So actually that project covered 4 subjects. One is software engineering, the other one is signal processing and mechatronics, third one is distributed embedded systems, and fourth one is advanced digital design. So there were 3 main tasks of the project. The first task was, here you can see a pendulum. So we had to stabilize inverted pendulum so that it should come here. Now here we can see that this system is inherently unstable. It can never stay over here. So our task was to stabilize it over here using 2 methods. One was using simulating control using MATLAB from the computer, and the second controlling method was using embedded control, where we used ARM processor as an embedded processor. So this was the first task, and second task was to build a graphical user interface in MATLAB. Here we have developed this one so that which can show the real-time representation of the pendulum system. Here we can see that the pendulum is moving and it is showing the real-time simulation. Though the system is on, it is not stabilizing it, but here we can see the movement. If for example if you focus on the pendulum, I am bringing it at the right position. Now if you just focus on the graphical user interface, see it shows the real-time position of the pendulum. Now apart from showing the graphical the real-time graphical user interface, the display should also have other features. For example, it should record the real-time simulation. Now we have a record button which records it and then saves it in XLS format, like in Excel sheet or etc. Then we have, and what does it store? It stores the time and similarly the pendulum angle and the position of the card. Then we have the offline mode, where we have a start simulation button. It shows the simulation of the pre-stored data, etc., etc. Now we focus on the hardware. We have pendulum. Here we have 2 sensors, and both of them are the optical encoders. One is a horizontal position sensor, and the other one is the sensor for the angle of the pendulum stick. Now we have an amplifier over here, which is used to amplify the control voltage which is supplied to this cart and the motor, and we can see that it provides 2.5 volts to the motor. If we connect this one and we just don't connect it, it provides 5 volts. So the gain is about almost 5 times. Then we have over here a calibrate button, an off button and off button. Now I have already calibrated it, so that calibration is important in order to have the 0 position, and I have calibrated from right side and in the downward position. Then we have the sensor data is actually sent to the FPGA board, where this data is routed from the SPI interface to the ARM processor board, and from ARM processor board through the serial interface to the PC, where the data is collected in the hyperterminal and the data is shown in the graphical user interface. And the second thing is this, that the control voltage comes from, in the first case, from the National Instruments card to the parallel interface from the PC, and it is directly fed to the motor. The second case will be that the control signal will be coming from the ARM board. I have started the real-time workshop over here. Now just gonna show you how does it work. I'm switching it on. Can you please just
yeah.
So here you can see that it's going to stabilize itself using the simulating control. And here you can see in the graphical user interface, it is also showing the exact position of the pendulum. Now here you can see that the pendulum is stabilized within 5 seconds. Now it is stabilized here, you can see. So using simulating control. Now if I give a small jerk over here, still it will try to stabilize itself. See? It has become a bit unstable, but it will stabilize itself. So, and this was using it is stabilizing using Kalman estimation using MATLAB and Simulink. Again, if I just try to disturb it, it will try to stabilize itself. See, it stabilizes itself. it takes a bit more time, as was specified that it should stabilize itself within 15 seconds. Sometimes it does stabilize like within 5 seconds. So, okay, so the next step was to stabilize this pendulum using distributed control. Then we used 2 ARM processors. So what were we doing? We were actually collecting the sensor data from one ARM processor, and that ARM processor sent that sensor data to the another ARM processor using this port, and it used controller area network CAN. So we had a CAN control over here, and this other controller calculated the control signal accordingly and send it back, and then it applied the voltage, so that we had a network of distributed systems, the embedded systems which were distributed and which were performing their real-time calculations. And here we can see in the graphical user interface, we can see the delay is very small. It is less than 0.05 seconds. So the error is also very small. And the next task, which we didn't do up to now because the time was less, was that to get rid of this ARM processor. We have an FPGA over here, so the task was to design our own processor, put it there inside this Xilinx partner FPGA, and that processor should control this inverted pendulum. But it's going to take more time. We tried, we designed a small processor, but it does not have those features, those processing features which ARM has. So we will soon develop that system. So here you can see the pendulum, stabilized inverted pendulum, which can stay for like hours. And if you just even give it a small jerk, still it will keep on stabilizing itself. Thank you very much.